Okay. Last few classes we are doing unsupervised learning, and unsupervised learning is basically where we do not have a target class. That is, we have the raw data, we have the features, but we don't know which class the data belongs to. Under unsupervised learning, a major part is clustering, and we have seen now two ways of clustering data. One is using exclusive clustering, the other is using agglomerative clustering. In fact, in last class, we tried to write the code from scratch for k-means, which is an example of exclusive clustering. Agglomerative clustering, earlier I used to do it from scratch, but now I feel there is no need. We can directly move on to using the library and then checking it out, because the code for hierarchical clustering is a bit complicated and the end result is similar. Maybe we can move ahead and we can look at this part. How do we choose, or what is the metric that we know tells us that the clustering solution is good or bad? Okay, so if I have multiple clustering solutions, how do I compare which clustering solution is good or bad? Okay, so for that we can discuss this. So how do you validate your clustering? So there are two ways, or there are two problems in that. First is, how do you decide the optimal number of clusters that fits the data? So we saw earlier that this actually is very subjective to the data we are looking at. It is very subjective to the domain we are looking at, and it depends upon so many different factors. So it is difficult to say what is a good cluster and what is a bad cluster. At least we have not seen a metric so far. And the second problem is that we see that there are various clustering algorithms and they behave in different ways depending upon two major factors. One is the features of the dataset, that is the geometry and density distribution of clusters. And second, the input parameter values. So like for k-means, we can choose what are the clusters we want, or for agglomerative, we can choose what is the, how do we choose what is the linkage between the two? Are we going for complete linkage, short linkage, word linkage, and so on? So depending upon these features, we may end up with different clusters, and which clustering is good or bad is difficult to tell. So how do we know which clustering method is better or suitable? And we need some clustering quality criteria. Okay, so can you think of something, or how can we know if we have a good cluster or bad cluster? Any idea? Okay, let me probably show you two examples, and we can then discuss on that. If I say that this is our data, okay, and we form clusters like this. Okay, do you think this is a good cluster? Absolutely not, right? And we take the same data, and let's say we say cluster 1, cluster 2, cluster 3. Okay, and in the second case?
Yes.
Okay, now do or how could you say the first cluster is bad, and how could you say the second cluster is good?
Here we can see the distance.
Distance.
Distance between these points in the first clustering is very large.
Okay. Distance between what points is large?
The points in one cluster.
Okay. So, a very interesting observation. What you're saying is, in the first, actually, wait, let me create 2 copies of it. Okay. So, very interesting point you're saying is here the distance between the points of a cluster. If I look at maybe the net distance across these points, and if I look at net distance across these points, I can say that here in this case, this distance is more and this distance is less. And that is one hint in which we know that this is a better cluster than this one, right? Excellent observation. Any other observations? So that is one part, which is correct. I'm looking for one more answer. How do we know that this one is a good cluster and this one is a bad cluster? Okay, let me give you another hint. So if I take this cluster itself, and between these two clusters, between these two examples, if I say uh, now, if you had to choose between, let's say, this example and this example, which would you say is a better cluster? A or B?
A.
A. Why?
Because the distance between the cluster is more, so we can be sure that that cluster is proper.
Oh, excellent. The distance between the clusters is more, and then we can say that
And
this
then,
is better. Did you say something, Anand, after that?
sorry?
I did not hear what is the last part you said.
What I mean is, between the clusters there is no outliers, and it is proper, and there is F. So we can be sure A is
Right. Excellent.
more correct.
Excellent. Excellent. If you have to come up with terms to explain these two concepts, okay. One concept is the distance between the points within a cluster and the distance between the clusters itself. What term would you say?
The cluster density.
Cluster density.
Point.
Okay. Yes. Cluster density is a good word. Okay. Anyways, that guessing that is to guessing that right in that way is to. But excellent. We found two criterias to measure if we have a good cluster or not. Okay, let us go ahead. So to explain this, there are two words actually. One is called as intra-cluster density. That is the density or intra-cluster distance or intra-cluster similarity, and that is basically if I take the distance between the independent points within a cluster, what is the variance that I have? Okay. So let's look at this. So for a good cluster, we should have high intra-cluster similarity. And again, for a good cluster, we need to have low inter-cluster similarity. Okay, high intra-cluster similarity and low inter-cluster similarity. What does this mean? High intra-cluster similarity means all the data points are close to each other. That means they are very similar to each other. Or we have something called as low variance among the intra-cluster members. Okay, they don't differ too much. The members of one cluster, they are very similar to each other. Thus, we will know that they all belong to one cluster. Okay, we can evaluate that using our variance formula. This is a modified way of the variance formula, but instead of dividing by n, we are dividing by n minus 1. Okay. Here you're just saying that if I take the mean of all these intra-cluster points, from those mean, if I subtract the distance or if I see the distance of individual points, so that is the sum squared error, and divided by n minus 1, I have this term, which tells me what is the variance between the intercluster points. Okay, and what we want is we want low variance. That is, we want all of these errors to be very minimal. So the closer the intercluster points are, the better for us. The closer the intercluster points is another way of saying high intracluster similarity or low variance. The second thing is, in general, good clusters should have low intercluster similarity. That is, if I look at two clusters, they should not be similar. They should be very far from each other. Okay, and that is a good example of a good cluster. So low intercluster similarity means high variance. That is, the clusters do not look, the members of individual clusters, they don't look like each other. Okay, and there is a metric that we have that combines both of these ideas together. It is called as the Davies Bolden index. Okay, so one good measure of clustering quality is the Davies Bolden index. So we'll see how it is evaluated. So Davies Bolden index is basically a function of the ratio of the sum of within cluster, that is intra-cluster scatter, to between cluster, that is inter-cluster separation. Okay. So it is a function of the ratio of the sum of within cluster scatter to between cluster separation. So let's look what this looks like. So if we have C, that is C1, C2, C3, Ck as the different clusters of n objects. So here, let's say there are two clusters of approximately 25 different objects. So that is what we mean the clusters. Then the Davies Bolden index is given by this formula, which is 1 by k summation 1 to k Ri, where Ri is equal to the max of Rij. So we have a matrix Rij, and the max of Rij is Ri, where j takes different values 1, 2, 3, 4 till k, and we know that I is not equal to j. So we are looking for not the diagonal components, we're looking for the off diagonal components. Okay, anything that is not diagonal. And how do you evaluate Rij? We say, okay, Rij is evaluated using this. That is the variance of clusters I plus the variance of cluster J divided by the norm of Ci minus Cj. Okay, and what is Ci Cj? Ci Cj are the centroid of the clusters. So if I just look at this term, to have a big number here, we should have we should have high numerator and low denominator. Okay, to have a big number of Rij, we should have a high numerator and low denominator. So when I say high numerator, it is the addition of the variance of multiple clusters. Okay, so here if I say the variance of this cluster is basically a measure of uh, uh, it's a measure of similarity. So for high intra-cluster, this will be, I'm just thinking when I'm saying, for high intra-cluster, this is low value actually, and divided by inter-cluster similarity. So inter-cluster similarity, these are very far. This is also low. So this denominator here, yeah, okay. Okay. So both terms come out to be, for a good cluster, both these terms would come out to be low. It is now difficult for me to analyze how Rij will be higher. Nonetheless, this is the formula for Davies Bolden index. We'll try it for different clusters and we'll see how the value changes. Okay. The numerator Rij is a measure of intra-cluster similarity, while the denominator is a measure of inter-cluster separation. Okay. So they put these values inside, and thus once we have that matrix for each, we have to find the maximum of that matrix, and the maximum of that matrix gives us the Davies Bolden index. Okay. We'll have to try it and see how things turn out. Okay. Okay. Nonetheless, what we have seen so far is we have seen what is clustering. We have seen major approaches on how clustering algorithms work and how to differentiate between them. We saw two algorithms, the k-means algorithm and hierarchical algorithm. And we saw to compare exclusive and agglomerative clustering, what are the major problems with clustering techniques. And we saw how to define and use a cluster validity measure as a Davies Bolden index. Let's look at an example where we will work on a data set for clustering, and then we can take it in. Let me share my laptop screen. I'll load the data set first. Just give me a moment. Okay. So let me go through this notebook and I'll explain what the data is. So this is basically a student's survey data, and we are trying to find out if by looking at the responses of the students, how we can cluster this data together. So let me go to the first few steps. We load all the packages, commonly used packages, pandas, numpy, matplotlib, cbon, so on. If I do an ls on my folder, I know that I have a file called as description.txt, and I have got this CSV, which is Turkey student evaluation. If I open or if I print the contents of the description.csv, it gives an idea of what are the attributes available in the data. Okay. So the attributes available in the data is instructor. So instructor, there are 3 values, 1, 2, and 3, representing 3 different teachers, 3 instructors. Then we have a class code, which is a course code that takes values from 1 to 13. So there are 13 subjects. We have a variable, we have a feature called as repeat. That is the number of times the student is taking this course. So that means has the student taken this course before, and for some reason they were not able to clear it, uh, uh, and now they are taking it again. Okay, so like this, what is the number of times that they have already taken the course? So someone with the value 3 is someone who has already taken the course 2 times and not cleared it, and the 3rd time you're trying it. 0 means they have not taken the course at all. 1 is that's the first time they're taking the course. Okay. Then we have a variable called as attendance, and that gives us some level of significance in terms of are they regularly attending the classes or not. Okay, so the value of 4 says that yes, they are fully present or fully regular. That's the highest score that we have, and this is somewhere in the middle, and 0 is where they have not attended at all. Then we have level of difficulty, that is according to them, according to the student, what is the perceived level of difficulty of the course. That takes values from 1 to 5. Okay, so these are basic information regarding the student, the instructor, the class, and so on. Following that, we have 28 questions, and these 28 questions can have values from 1 to 5. Let us look at some of these questions. So let's say question 1 is the semester course content, teaching method, and evaluation system were provided at the start. So a high value here means the teacher has explained the entire course content. He has set the rules for the classes and told how they'll be evaluated or not. And low value or a value of 1 is probably where the teacher has not explained these ideas. Okay, let's look at another question. Maybe question 14, the instructor has come prepared to the classes or not. Question 20, the instructor explained the course and was eager to be helpful to students. So there are several questions that are asked for each course, for each instructor. And then we are trying to analyze the response of the students, and we are seeing what we can do about it. So here, if you look at this data, there is no target class, or at least in the terms that we understand, there is no target class as such. Okay, so let us load the data. I read the CSV file into a variable called as dftrain, and these are the different columns. If I do a dftrain.shape, we can say that there are 5,820 rows and 33 columns. If you want to see, let's see how the data is. So I'm doing the data exploration phase now, where we are exploring what our data looks like. Are there any anomalies, missing values, and so on. So first we do a count plot on the instructor for dftrain, and this is what we get. Looking at this plot, do you have any observations? What can we comment upon the data?
The third instructor has more responses.
Right. What can we conclude based on that?
Might be the course that the third instructor was teaching was interesting, or the instructor was very good at teaching. The count indicates the number of students that gave the responses.
Right. Then the number of count is the number of students that gave responses. So in that, okay, you're saying course instructor 3 may be interesting, so many people are attending his course. Okay. Any other observations? Anand, you were saying something? Okay. Let me bring some alternate views. It could also be that the class size of instructor 3 could be bigger than the class size of the other instructors. Or we could have, out of the 13 subjects, instructor 3 takes many subjects, and instructor 1 and instructor 2 take less subjects also, right? Those could also be possible explanations of why we have more number of data points for instructor 3 and lesser for instructor 2 and instructor 1. So nonetheless, let's keep this in mind. Let's go ahead and look at some other things. So how are the responses distributed over classes? Okay. So for each subject, how many different responses we have. So I'm doing a count plot in terms of class. We now know that there are 13 classes, and these are the number of responses for each of the classes. Looking at this, do we have any observations? So what was the most attended class? Or what was the class? Yes, 3 and 13 that we had most number of responses for, and least
2 and 12.
Okay, 2 and 12. Great. Now the next interesting question would be which classes were taught by which instructor? Okay, which classes was taught by which instructor? How do you think we can find this answer?
Group based on class and instructor.
Excellent. We'll group based on class and instructor. That is exactly what I did. So I said, okay, take DF train, group by the class, and for the instructor, find the median. Okay, I'll have multiple values. I'll find what is the most common value or what is the centermost value, and that will give me the answer. So by doing that, we see that this is the distribution. Classes 1 to 13, these are the instructors. Now I would difficult to count, so I just took this. Not very difficult actually. This is very easy to count which classes were taken by which teacher. But if you want to do it programmatically, then I'm putting this into a loop, taking this the same answer into a variable called as class by instructor. And when the class by instructor is 1, I see classes 2, 7, and 10 are taught by instructor 1. Classes 1, 6, and 11 taught by instructor 2. And classes 3, 4, 5, 8, 9, 12, 13 plus taught by instructor 3. So this explains for us why we had more number of data points for instructor 3. He was teaching most of the subjects. Okay, let's go ahead. Next, what I'm doing is I want to know what is the average response of a student for each of the questions. Okay, what is the average response? So I first take a subset of the bigger data. That is, take just the questions. So column number 5 to 33 are the 28 questions that we have. I take that into a variable called as x underscore questions. And for each of the questions, you're finding the mean value and converting that into a data frame, doing a reset index. So I'll have a data frame in fact. And for the data frame, we can do a bar plot. Okay, so by doing this, we see that for the 28 questions, this is what we get as answer. So from a rating of 1 to 5, most of the values are around, most of the values are a little above 3, and all of them are under 3.5. Just one value here for question 1 is less than 3. Okay, so that gives me an idea that we have a general, what we have is we have a general response of average. We have an average response for all the questions, where the mean value is 3.18 and the standard deviation is 0.109. Great. So our interest is to basically cluster these 5,820 points into different data sets, and we want to see, uh, can I cluster this data in different points? What could be the advantage of clustering the survey data into different points? Any ideas? Okay, so let me answer what I understand of what could be the advantage. The advantage is, if I divide the cluster areas into, let's say, 3 points, if I take all these points and divide it into three groups, uh, people who have given low average, people who have given high average, and people who have given medium average, we can target them separately. So the goal of the university would be that all of these values, all of the survey points go to the higher level. So we can probably, based on what uh, the happy students are saying, we can see which instructors are doing good, and we can take the best practices of those instructors and uh, create a rule or create a guidelines for all instructors to be able to follow what instructors with high ratings are doing. And if we take a cluster of lower end students, we can take their we can talk to them and talk to these guys and find out what is the bad qualities of uh, uh, which questions some instructors have fared the least, and based on that do some rectification again from the data, and see that which how these instructors can improve, so that the net score goes on the upper end. And depending upon if we have multiple repeats of students and what is the course level difficulty they found, we could also find some prospective candidates for students who would require counseling within this field. So counseling, maybe the course is not a problem. Their personal interest in the course is a problem, so they would require counseling in terms of career guidance or some other issues and so on. So we could look at this data and do several things with it. We limit our what do you say, our exploration to only clustering, and see how we can cluster this data and how we know if it is a good cluster or not. Okay. So with that in mind, first let us find out if there are any missing values. So if I do dftrain.asml.sum, I see that 0. So excellent, no missing values. A major, okay, this is a great point. So for us, if we look at, let's say, just the questions and their 28 dimensions, it would be impossible to plot it, and it will be impossible to plot it and visualize how this data looks like, right? And if it is impossible for us to visualize and see how this data looks like, then even when we form the clusters, we will not be able to see what the clusters seem like, and if at least visually we are able to find out if there's a good cluster or not. For that, we'll be using an algorithm called as PCA, which is Principal Component Analysis. And what PCA does is we can use it, in this case, we use it for dimensionality reduction. That is, we will reduce the number of dimensions of the data. And PCA basically takes all the features and combines them in different ways, so that we can capture the maximum variance of the data. So earlier we have these 28 questions, 1, 2, 3, 4, 5, 6, 7, 8 till 28. And what it would do is it will have feature 1 as the weighted sum of all 28 questions, feature 2 as weighted sum of all 28 features, and so on. And every time the weights are played around in such a way that we will try to capture the maximum variance within the first few features. So the advantage of that is, as you go on adding features, you will see that less and less variance is available in the later features. And when less and less variance is available in the later features, then we can safely remove those data points, remove those features, and still have most of the data being represented in the first view. Okay, let me show you an example of that to make this more clear. Okay, so I load PCA from scikit-learn's decomposition module, and I load also k-means from scikit-learn. Okay, from scikit-learn cluster we take k-means also. We take the X, which is our entire data set for only the survey questions, features 5 to 33. If we look at x.shape, we can see that there are now 28 rows, 28 columns for the 28 survey questions and 5,820 rows. Okay, the PCA that we had loaded, I am saying that I want from the PCA, I want just 2 components. And I create an instance of that object in something called as this PCA underscore dimred for dimensionality reduction. And I fit this data. I fit the data that we have, that is PCA dimred dot fit transform x. Fit transform is the standard way for scikit-learn to fit the model and use the model also. So we are fitting it using this x, using the model, getting our answer as x PCA. And if you look at the shape of XPCA now, we can see that XPCA does not have 28 columns. It has just 2 columns. Why 2 columns? Because that is the number that we chose here. We want to see with these 2 columns, what is the variance that we have captured from the 28 columns. Okay. So if I look at PCA dimred dot explained variance ratio, I can see that out of the 2 features, feature number 1 captures 82.19% of the variance. So almost 82% of the variance of all the 28 data is captured within this one column. The second column has a variance of 4.5%. Okay, so what we see is out of the 28 questions, we have captured most of it within the first column itself. And as we go to as we increase the number of PCA, we could see that this number will become lesser and lesser. Okay, so if I do the sum of this explained variance ratio, I can see that together these columns 1 and 2, they give a total explained variance of around 86.7%. I could also now would say probably let me try increasing the number of PCA components and seeing how the explained variance changes. Okay, so if I change this to, let's say, 10 columns, and if I look at the explained variance ratio, I have to run all, is it? Let me do this. Okay, we can see that if I have 10 columns, how the explained variance changes. The first column has 82, second column has 4.5, third has 1.4%, then 1.2, 1, 0.9, 0.7, 0.6, 0.6, 0.5. So as we keep on adding columns, each additional column adds a delta change, and the delta change is smaller than the previous column that we had. Okay, so as you go on increasing the columns, we see that the variance that they capture is lesser and lesser. Okay, so in our case, we will limit to 2 dimensions, and the reason for 2 dimensions is thus we will be able to plot the data. Sorry, we'll be able to plot the data, and we will be able to visualize how the data is distributed. Okay, so that is our agenda for coming to 2 columns. So now XPCA represents at least 86% of our data, and we want to see how this data is distributed. Okay, so if I do a simple PLT dot, if I do a scatter plot on this, I can see that this is the distribution of my data. PCA 0 is on the x-axis, which captures most of the variance of all the data points, and PCA 1 is on the y-axis, that captures again just 4.5 variance of the data points. So looking at this, we can probably see how the data is distributed. Now PCA 0 or PCA 1, they have lost meaning in the sense that we cannot say that PCA 0 is the first 14 questions or something like that, or in fact, we cannot talk anything about the distribution of PCA 0 and PCA 1. So they are just new features created from old features. The old features have physical or some significance. The new features are just mathematical formulations of the older features. Okay. So in this data, if I visualize it this way, and if I want to divide it into clusters, I would probably say it is difficult to cluster it out because they are not neat divisions. But I would cluster something like 3 points. If I have to do, I would say this would be section 1, cluster 2, and
Aditya,
cluster 3. Yes, Switcha?
I didn't get it properly. All these 28 questions are combined and they are formed into this PCA 0 and PCA 1.
That's right.
Okay, fine.
Yeah, all these 28 are combined together. So PCA 0, as I said, it is difficult for us to see how this combination will work out. So some combination of all these 28 questions is PCA 0, and some combinations of all these questions are PCA 1. And the agenda is we see that PCA 0, in fact, captures 82% of the variance of the 28 questions. So they are what we say. They are a lot representative of the 28 questions.
This 82% indicates that it doesn't include all 28. It is including some most or...
No, 82% indicates that it is able to capture 82% of the variance of the 28 questions. Means, of course, it is not all, it is not everything, but it is 82% is a huge percentage, right? So that is what is showing. But we cannot say that 82% means out of the 28 questions, we have taken 82 questions, 82% of the questions, and we have left out some questions. That is not what it says. What it means is all 82 all 28 questions have been combined together, and just the first, the zeroth column of the PCA is able to capture 82% of all the data points. Okay, maybe next class what I'll do is we'll go on the maths of PCA. That will explain to us some more clarity. Here I'm directly using it as well. Nonetheless, let us see if I have a data distribution like this, and if we try to now cluster this data, what do we get? So first, let's try fitting the k-means for 2 clusters. So from scikit-learn, I'm just taking k-means in clusters as 2. Take the XPCA, that is, take the reduced version of our data sets. And on this reduced version, if we try to fit the model, and then we try to predict the answer, we can see that the model gives zeros and ones. If I now try to plot this data, I can see that k-means has divided the cluster somewhere in the middle, and we say this is cluster 1 and this is cluster 2. Let us now, probably with k-means, it is difficult to tell if the number of clusters are right or not. What we could do is we could try several clusters. So here I'm trying cluster 1 to cluster 10. And for each cluster, I have a measure called as the distortion of the cluster. Okay, so that is, we find something called as the inertia of a model, and I keep on storing the inertia into this variable called as distortion, and we will see what the distortion changes when I add more and more clusters to this data point. So when we do that, okay, we see that these are the distortions. That is, distortion probably is a measure of what do you say? Is a measure of variance of the data. Okay, so if I take all the data points, I have the highest variance. As I go on increasing the number of clusters, of course, the variance will keep on becoming smaller and smaller because now I'm looking at a smaller set of these data points. But if I plot this data, if I plot this data, we end up with a line chart like this. Here we have, with one cluster, this is the inertia. With cluster 2, this is the inertia, cluster 3, cluster 4, and so on. As we go on increasing cluster, we can see that of course, our distortion measure or our inertia keeps on becoming smaller. The way we choose what are the number of clusters good, or one of the ways is called as the elbow method. And the elbow method is it's actually highly debated how we choose from the elbow method and if it is a good method or not. Nonetheless, what the method basically says is we want to choose that cluster point after which the variation does not change too much. Okay, so we are hoping an ideal elbow point would be something like this. I move down fast and then I move slowly. Okay, so just like our elbow, we would say that this would be the upper arm section, and after the elbow, this would be the forearm section. So we are looking for that point where we have a huge variation in the first part, and then after that, less variation, and that point that we have, we say is the right number of clusters to choose. So in this case, based on elbow method, I would go with saying that 3 is a good point, because before 3, I see a huge variation. So from 23,000 to somewhere around somewhere around 38,000, we come very quickly, and then from 38,000 to 7,000 or 8,000, we are moving very slowly. Okay. So keeping that in mind, I would choose K as 3. But as I said, this is a highly debated topic in terms of is it a good way of doing things or not. Nonetheless, let us choose for our case 3. And if we do the same fitting as before, and we do it for 3 cluster heads, we can see that this is the kind of division we get. So this is cluster 0, cluster 1, cluster 2. Okay, so the difference between this part is now I'm clustering the data into 3 groups, but I'm using only the XPC, that is the reduced version. That is just the 2 features, the 2 artificial features that we have. Based on that, if I cluster, I get this response. And in the second case, I am clustering over the entire data set, that is all the 28 questions. So even though I'm clustering over all the 28 questions, uh, uh, and the answer y1 is the cluster value based on the 28 questions, I cannot visualize it, right? So I'm plotting this with XPCA, but the clustering has been done using all the 28 features, not the reduced version. So if I do it that way, that is clustering based on all 28 features, this is what my data distribution looks like. And with XPCA, this is what the distribution looks like. And you could see that most of the distribution is very similar to each other, right? That is, we have roughly the same division between the data points. And this is just a fact that we would also expect this, because PCA is also is just the same data represented in a different form, and we are capturing, at least combined with PCA 0 and 1, we are capturing 86.7% of the data. So the clustering would be similar. Let's go ahead and look at the confusion matrix. That is, if I say the clustering based on PCA and the clustering based on all the data points, how many clusters have changed? Okay. How the values have changed. So if I do a confusion matrix, I can see that for uh, for the true value, I'm using the actual clusters, that is all the 28 features. And for the predicted values, I'm using the features based on, okay, sorry. For the true values, I'm using PCA features. And for the predictions, I'm using these features, what do you say, the original features, to all 28 features. In that sense, I can see that for this row, the PCA features are telling that 3 data points belong to, so okay, the way we would read this is these are the data points that PCA tells belongs to cluster 0, that is 2224. And out of these 2224 are all features say that these very data points, that is 2221, belong to one cluster and 3 belong to another cluster. So only these 3 points have changed in terms of first row. In the second row, uh, we have 1239 talked as one group, and here we have these 1239 and 1 additional, so 1240 is one group. So we in fact have only 4 changes, at least in this run that I have. I see that only 4 data points have changed clusters from PCA model to the whole model, which gives us a good proof that PCA is actually a very good representation of the entire data set. That is, only 4 values out of 5,820 clusters have changed their groups. Apart from that, all the clusters, all the data points belong to similar groups as before. So this was an example using k-means. Let us quickly look at an example using agglomerative clustering. So I will not execute this, I will not run this because agglomerative clustering actually takes a lot of time to finish. I think this dendrogram we found to get an answer to this, I had to run the code for at least 4 to 5 minutes, which is quite slow for just 5,000 points. So for agglomerative clustering from scikit-learn.cluster, I take the algorithm called as agglomerative clustering, and we use sci-fi. From sci-fi.cluster we take hierarchy, and this hierarchy will help us to plot this dendrogram. So we take a copy of hierarchy in higher, and I say that okay, take the higher, okay, what will be the measure that we'll be using for our inter-cluster distances. So inter-cluster distances will be measuring using the WOD method, and I just create an object of that into this variable called as dendrogram, and then we plot the dendrogram and we see this plot. So you see that our hierarchical clustering gives us this plot, and this plot dendrogram is very easy to interpret. If I want 2 clusters, I will cut somewhere here and say this is cluster 1, this is cluster 2. If I want 3 clusters, I will cut somewhere here and I'll say this is cluster 1, and everything below this point is cluster 2, and then below this point is cluster 3, and so on. So that is how we would divide the clusters. Nonetheless, I don't need to cut it manually. I can take these points. I can directly choose the number of clusters I want using agglomerative clustering. This takes a bit faster. So I have to load this first. So if I say I want 3 clusters using agglomerative clustering, and then I fit and predict the model for Y, and then we plot the data, we can see that agglomerative clustering gives me this kind of a plot. Okay, so we see that there's a lot of overlap between data points. That is, we don't have a neat cut. We see some mixture here, we see some mixture here, and we see that for this data set, for this cluster, we have very less points. So, which was actually expected here. You see, in this cluster, you would have less number of data points here, and that is what we have from agglomerative clustering. If I do confusion matrix just to see how data points have changed, so I can see that a lot of data points have changed between the 2 cluster models. For Y2 is the clustering using agglomerative. We can see the columns. So the third column here just has 769 data points, and we have here around 2500 and here around 2500. So out of the 5800, we say 2500, 2500 and 800. That is how agglomerative clustering has divided the data, whereas k-means roughly divides the data into a similar number of points. Which clustering is better? So let us use the Davies Bolden score. So that can be taken from scikit-learn sklearn.metrics, import Davies Bolden score. And I just try for X data and Y1. So Y1 is our clustering model with all 28 questions and k-means. and Y2 is a clustering model with all 28 questions and agglomerative. And we can see between the two that Davies Bolden score for k-means is higher, that is around 84%, 84.84, and the Davies Bolden score for agglomerative is less, which is 0.77. So we get some sense of an idea that probably the k-means clustering is better than this one, at least in terms of intra-cluster distances and inter-cluster distances. Okay. Okay. Do you have any questions?
Small doubt. In
Yes.
agglomerative clustering, if you see the right side, the group 2, there are few number of points. From visually we can see there is the cluster is small. But in K means it came proper, means it went more left side.
Mm-hmm.
But why the reason it happened? That it should be like this agglomerative cluster, right? Should have.
Uh, the philosophy of clustering is different between the two clusters, right? Uh, what uh, what agglomerative does is it will start, it will take a bottoms up approach, and it will look at the closest data points and start joining them into clusters. So it's actually very difficult to say why agglomerative has done it this way and why k-means has done it this way.
So in the initial point or run again, it will be the same. The
Yes.
initial point has some factor, right?
Yes, k-means has a factor of initial points, but if you remember the last case that we saw that even with different initial points, our k-means was, if there is a good pattern in the data, k-means gives us more or less similar answers always. Okay. If there is no pattern, then also k-means does a good job in dividing equally. So I think k-means is biased towards equality in terms of how the data is clustered, in terms of distance as well. But agglomeration does not have that criteria, because it just tries to put different hierarchies over the clusters. So in this case, I am not sure if agglomerative is good. So one more reason I don't think agglomerative might be a good answer for this data set is agglomerative generally works good if the data has hierarchy within. That is, if let's say out of the 28 questions, we have questions 1 to 5 come under one group. Questions 5 to 10 come under one group. Like if there is grouping between the questions also, then agglomerative can capture that grouping well. But in this case, I see that all 28 questions are maybe not related, or they are just distributed randomly. So I'm not confident with agglomerative in that sense, because I understand that the philosophy how agglomerative divides the clusters is different from what k-means does. And in this case, since I would say that the data does not have an inherent hierarchy within it, agglomerative may not be a good solution. And we get the same confirmation using Davies Bolden score also, right? Now, your question is why agglomerative is doing this way. It's very difficult to answer that question. We cannot, or at least at this point, I do not know how to answer that.
Yeah.
You understand, right? It is,
Got it.
yeah. We have to look at individual data points and see how they're grouping. It's actually very complex to answer that question. Okay. So additionally, unsupervised has this additional problem, that is, it's very subjective. So probably someone who has spent some time within the domain on how survey data work out, and specifically in this survey data also we have just 5 options, right? 1 to 5. So many data points would be close. So here, in fact, you see this, when you look at these points, this plot does not look like 5,000 points. It looks much lesser. It looks maybe hundreds of plots, maybe. Right? And the reason they look much similar, I think, is because if you look at, even though we have 28 questions, all of the questions have only 5 options, and many of those options will overlap on each other. That is why this plot does not look like 5,000 points. It looks much lesser than 5,000 points, maybe 400, 500 points and so on.
Okay.
Okay. So we'll stop here. Maybe next class. Unsupervised learning is actually a very what do you say? Uh, Again, it depends upon domain actually. So some domains have more use of unsupervised. Some domains have more use of supervised. Generally, what I've seen in my observation is people in companies or so on, they focus more on supervised learning because it is actually very measurable in terms of how good or how bad we are doing. Unsupervised is very difficult to measure. Though we have more data, we are still learning how to capture most in unsupervised learning. Okay. Maybe next class onwards we can start talking about neural networks and we can see how this works out. Okay, one more thing that I need to do is next class we'll also explain PCA. I think PCA is an important algorithm. We can even go to the maths of PCA and see how it works out. Post that point, we will start neural networks. Okay. Okay, then see you guys. Bye bye. Stop sharing and